Hello and welcome. We've talked a little bit about why control is necessary. Control is necessary for stabilizing unstable systems, for delivering on performance guarantees. How to control. We've talked a little bit about feedback as being the most effective mechanism for implementing control. Now in this lecture we'll talk a bit about what to control. Why is this question important? It's important because this is a key decision in the design of the control system, and this decision has to be taken because the number of control degrees of freedom or manipulated variables that you have in a process is fixed and limited, and therefore the number of process variables that you can control and regulate is also limited. This puts a limitation on the number of process variables that can be controlled. So if you have n manipulated variables, then each manipulated variable can control up to one process variable. So for n MVs you can control up to n PVs and no more. Therefore, because you are limited in the number of things that you can control, what are those PVs that are controlled must be chosen wisely. In this example, the only control degree of freedom is this heater duty, and this heater duty has little or no effect on OD, on the odor. If you increase the heater duty, the temperature increases and the air appears drier, so the relative humidity decreases. Now because the purpose of a heater is directly linked to the degree of heat that is contained in the air, and temperature is a direct reflection of the degree of hotness of a substance, therefore it makes sense to control temperature using QHDR. It makes sense to pair these. Now let's say such a controller is implemented. So we've seen this before. So you have this feedback loop. This feedback loop that maintains the temperature as close as possible to the set point by adjusting the heater duty. Now this controller, the process variable temperature is a single input that changes over time into the controller, and the output from the controller is the single manipulated variable that changes over time in response to the changes in the temperature. This is also an input to the controller, the set point, but this is usually fixed and doesn't change over time. So for example, for the user, a 20 to 25 degrees Celsius temperature room is comfortable. So this 20 or 25, let us say 25 is chosen as the 25 degrees Celsius is chosen as the temperature set point. This 25 degrees Celsius is not going to change over time. So when we are talking of inputs and outputs, we are talking about things that are going to change over time. So in terms of the controller takes in the process variable, the controlled process variable, as the input, and its output is the desired changes in the manipulated variable. Hence the term SISO, single input, single output, single input to the controller, single output from the controller. Now let us say on a particularly cold day, winter air is very dry. Now if you have a particularly cold day and you have your heater giving you 25 degrees Celsius, then what will happen is, because the dry air has been heated and no water has been added to it, the relative humidity of the air, the water content of the air remains the same, but hotter air can hold more moisture, so the relative humidity goes down and the air will become extremely dry, and in such extremely dry air conditions you can get things like nosebleeds, etc., which can be very uncomfortable. So the whole idea of the process of the heater and the control system is to have a room that is comfortable for the user, and here we have on a particularly dry winter day, the heating is actually creating a discomfort due to the extremely low relative humidity. So now in this case what we want is, we want to control the temperature, but we don't want the relative humidity to go below a minimum level at which people start feeling uncomfortable. So in this case what you would do is, if RH starts to go below RH min, then you got to switch, and what you got to do is, instead of the heater duty controlling temperature, now the heater duty will be adjusted to hold RH at RH min and temperature will float. So to clarify the point, here we have temperature controller adjusting the MV. Here we have the temperature controller adjusting the manipulated variable Q heater to hold the temperature. But in case the relative humidity goes down, what we would do is that the controller will adjust heater duty to hold relative humidity, and the temperature will float at a lower than set point value. Yeah, so this is what we are saying. And this situation is somewhat more complicated. You have a more complicated controller than a single input, single output controller. Now you've got two inputs to the controller, two process variables that are changing over time that are input to the controller, namely the room temperature and the relative humidity. And the controller adjusts QHTR in a manner so that if relative humidity is greater than RH min, QHTR is adjusted to hold the temperature. On the other hand, if relative humidity starts going below RH min or starts approaching RH min, control switches and the controller adjusts QHTR to hold relative humidity close to RH min. So when the normal situation is there where the controller is adjusting QHTR to hold temperature is fixed, relative humidity floats, and then when the switching happens, because the air has become too dry, relative humidity is fixed by adjusting heater duty and temperature floats. Yeah, so this is a more complicated controller, and it's got multiple inputs and a single output, hence it is called a meso controller. It's got two dynamic inputs, two process variables that are dynamically changing over time, and the dynamically changing output, you got a single dynamically changing output QHTR. It's a meso controller. You could have a still more complex control problem, and you may say, well, I am interested in holding both the temperature and the relative humidity. I want control over both. In that case, you need an additional manipulated variable to hold relative humidity. One such additional MV, common MV, is a humidifier. What is a humidifier? You blow air through a curtain of water, and so the air gathers moisture, and therefore it may be hot, but it has also gathered extra moisture, so the relative humidity is acceptable and it doesn't go too low. So you need an additional manipulated variable to hold the relative humidity, and this additional control degree of freedom could be, for example, the rate at which air is being blown through the curtain of water. This is schematically depicted here using this fan. I could not show the curtain of water, but the idea is you're blowing air through a curtain of water so that the air is moisturized, and therefore the relative humidity is what you want it to be and it doesn't go too low. And you could have two single input, single output controllers as shown in this figure. So what you have is the relative humidity controller taking in the relative humidity value, and based only on the value of the relative humidity, it makes an adjustment to the rate at which air is blown through the curtain of water. The temperature controller is also single input, single output. It takes in only the room temperature sensor measurement, and based only on its value makes an adjustment to QHTR. So this is two single input, single output controllers controlling two things, temperature and relative humidity, by adjusting the two control degrees of freedom that are there. Notice that what is controlled is determined by the function of the manipulated variable. The function of this W air, the air blowing rate through the curtain, is to humidify the air. So it makes sense to control relative humidity using W air. On the other hand, the function of the heater is to heat the air. So it makes sense to control the temperature, which is a measure of the degree of hotness of the air in the room, by adjusting the heater duty. So the function of a unit, the function of a manipulated variable, often determines the process variable that is controlled. So this is the case of two single input, single output controllers. You could also have a multivariable controller where the controller is taking in the two dynamic inputs, relative humidity and temperature. You have the two set points, temperature set point and the relative humidity set point. The multivariable controller does all the calculations and accounts for the interaction between temperature and relative humidity to make changes in W air and Q heater. What is the difference? The difference is I'm sorry. What is the difference? How in the world? Okay. Pointer options, pen. Okay. So what is the difference between two CISO controllers? In the two CISO controllers, please note, W air is moved based only on relative humidity, changes in relative humidity. QHTR is moved based only on changes in temperature. So in some sense, the relative humidity controller is blind to what the temperature controller is doing, and vice versa. The temperature controller is blind to what the relative humidity controller is doing. On the other hand, over here, W air is a function of both relative humidity and temperature changes. QHTR is a function of both relative humidity and temperature changes. That's the difference. This is called a multivariable controller. These are two single input, single output controllers. Economics plays a big role in determining what is controlled. Typically, if you want to maximize or minimize an economic objective, the maximum or minimum will usually lie at the intersection of multiple constraints. And let's just take a degree of freedom U. So this is your decision variable on the x-axis, and let us say at the nominal conditions, if U is varied, your economic objective varies as the curve, as shown in this curve. So the economic objective is varying like this. If there is a large disturbance, the shape of the economic objective curve remains the same, but it shifts a little bit up and down. So let us say this second curve is the altered economic curve for operation away from the nominal case. In either case, if the objective is to minimize J over the degree of freedom U, then one can clearly see that the optimal operation is always at Umax, because Umax minimizes J. So operate at Umax always. That's the optimal operating policy. On the other hand, you could have J varying like this, and in case there is a disturbance, the shape remains pretty much the same, but there are some shifts in the curve. In this case, the minimum in J occurs when U is at Umin. So you operate at U min always, that's the optimal operating policy. You could also have a case where in the room example, let us say you want to minimize your utility cost because heating consumes electricity, you got to pay for it, it's expensive, 10 rupees per kilowatt hour per unit of electricity consumed. In that case, if you want to minimize J, well, then T set point, the temperature set point, you want to minimize the Q heater rate. The optimum temperature set point is then going to be T min. So you want to only heat as much as is necessary so that you're comfortable and not overheat. Similarly, you got to hold the relative humidity set point at the minimum level that keeps the person comfortable, because if you increase the relative humidity by blowing more air, the air will cool down more, and so you will require more heat to keep the temperature at T min. Yeah. So basically you can see that for our 2 degree of freedom problem, the optimum solution that minimizes the electricity utility bill is holding temperature set point at the minimum comfortable level and holding the relative humidity set point at the minimum comfortable level. So this is an example of the optimum being at the intersection of multiple constraints. You could also have a case where there is an unconstrained optimum. So at the nominal case, the J versus U curve is as shown here, and the optimum value is, this is U optimum for the nominal case. Now in case there is a disturbance, let's say the J curve changes and now the optimum has moved from here to here. However, you're operating the process and you continue to operate with this value. If you continue to operate the process at this value, then the process was capable of operation here, but since you continued operating at the previous value, at this value, the J cost is this, and this is significantly above the minimum possible, and therefore this curve represents the loss from the minimum possible. So what this suggests is, in case the J curve shows an unconstrained optimum, a minimum or a maximum with respect to the degree of freedom that you have, then if that curve shifts a lot and the optimum is sharp, then you need to re-optimize as the process operating conditions change or as there are disturbances, and as the process moves away from the nominal case. So here you want to operate at U optimum all the time, but U optimum changes with disturbances, and therefore you have to track U optimum. So now control is required to track the optimum value of this decision variable U. So control for good economics, I'm just showing 3 cases. Let's look at the first 2. In these first 2 cases, you want to minimize J, so the optimum is at either the maximum value or at the minimum value, and if you want to operate at the maximum or at the minimum, and by the way, this hashed line shows that these constraint values cannot be violated. It leads to issues, or it leads to things that are unacceptable, such as safety limits, regulatory limits, customer guarantee limits. These cannot be violated. So these are in some sense hard constraints. These are also referred to as hard constraints. So if you know that a particular controlled variable, its optimum value is at maximum or at minimum, then what you need to do is control that particular variable as tightly as possible and then have its set point at CV max, or in this case have its set point at CV min. So tightly control all the constraints that are active at the optimum, make them CVs, because what to control is your choice, and then choose their set point at the constraint limit. That's in case the optimum is at a constraint limit. In case the optimum is unconstrained, I'll explain this a bit later. In case the optimum is unconstrained, then you need to track this optimum value for sharp curves, because sharp curves, you know, if the optimum shifts by a little bit, if the optimum moves from here to here, I mean the loss, you know, loss can be quite large. Okay. Now, why do you need a back off to avoid hard constraint violation? Here is the dashed line up here is the red line which can never be exceeded because of safety constraints, because of environmental regulatory constraints, etc. Now let us say the process variable is loosely controlled. If the process variable is loosely controlled, it will go all over the place, and if it is going all over the place, because you're not allowed to violate the top limit, the red line is not allowed to be violated, therefore you would be operating the process at a back off, and this is the back off. The average process operation is backed off from the constraint limit. If the control of the process variable is made tighter, then you have less variability in the process variable, and therefore the process operation can be moved, average process operation can be moved closer to the red limit, and your back off then is smaller. If you have nearly perfect control of the process variable, then the variability is negligible and your average process operation is almost at the constraint limit. Yeah. So this is the squeeze and shift rule. So if you have optimal process operation at a constraint limit, if the optimum corresponds to operating at a maximum or minimum constraint, then control that constraint variable as tightly as possible, and the tighter the control, the closer you can shift to that limit. In the next slide, show the same thing for two constraints. So this is constraint 1, this is constraint 2. Yeah, and the optimum is here at the intersection of these two constraints. Now if the control of these two process variables that are the constraint variables is loose, and these two limits cannot be crossed, then you can see my optimum operation is over here, and I am quite far away from the actual optimum. If the control of the constraint variables PV1 and PV2 is made tighter, then the optimum operation can be made to move closer to the actual constrained point, actual optimum. So this is the optimum point. So by squeezing the variability in the constraint variables, the process operation can be pushed closer to the constraint limits. This is the idea, or this is the motivation behind tightly controlling constraints, active constraints at the optimum. Now you could have degrees of freedom that are unconstrained, and like I told you, corresponding to every unconstrained degree of freedom, what to control is a choice that the designer makes. So I could control a process variable that shows a very sharp curve. So this is quite sharp optimum, and this is the optimum value. There comes a disturbance, the optimum moves, and if I don't re-optimize, I am operating at a loss, and the loss is significant. Now imagine I change the variable that I am controlling corresponding to this unconstrained degree of freedom. In that case, imagine this is the nominal curve for J, and then with a disturbance the nominal curve shifts, but you see the optimum value remains pretty much the same. So now if I do not re-optimize and I continue to operate at this old optimum, the loss is negligible. Negligible loss. So if I continue to operate at the same optimum value at the nominal condition, even for the disturbed case, I am near optimum. The process operation is near optimum. And so what you want to find out are those magic process variables whose optimum remains invariant with disturbances. The optimum remains nearly the same. These invariants is what we are looking for, and smart guys will be able to figure out smart variables which when held constant ensure near optimum operation. Yeah, so this is one way of managing unconstrained degrees of freedom that show an unconstrained optimum. That means the optimum is neither at a maximum nor a minimum, but somewhere in between. Yeah. So just to explain or highlight this concept of magic variables or invariants, I take the Kaistha example, running. So let's say you're running a 100-meter sprint, and running effort is the degree of freedom that you have in your hands. What is the optimal operating policy? You want to minimize the race completion time. That's the objective. Well, it's quite obvious. 100-meter sprint, what is the optimal operating policy? Run as fast as you can. So run at 100% effort. Put in all the effort that you have and run for 100 meters, and that will minimize your race completion time. So this is an example of a degree of freedom that is constrained at maximum. Now consider the same runner. Degree of freedom is running effort, but now you're supposed to run a 40-kilometer marathon or a 20-kilometer marathon. And again, the objective is to minimize the race completion time. And one may say, okay, instead of 100% effort, maybe what I'll do is I'll run at 30% effort all the time. So my operating policy is constant effort, and the constant effort value may be 30%, let us say. Is this the best way of doing it? We all know by intuition, no, this is not the best way of doing it. So another fellow may say, okay, I will adjust my running effort so that my speed is constant. My running speed is constant. So the runner is holding the speed constant, and now the speed set point is, let us say, I don't know, 10 kilometers an hour. You run at a constant speed of 10 or 12 kilometers per hour, maybe 12. Is this the best way of running the race? We all know that's not the best way, because when you're running uphill, better run a bit slow, otherwise you'll get too tired. You'll run out of gas. On the other hand, if you're running downhill, run a bit faster. Don't keep the speed constant. So maybe you say, okay, this is not the best policy. What I want to do is my level of tiredness. The level of tiredness may be as reflected in my breathing rate. If I'm more tired, I'll be breathing heavier. So keep the breathing rate fixed. Somebody may get smarter and say, well, even this is not the best. What we should do is we should adjust the breathing rate so that the lactic acid level in the muscles, which is what determines lactic acid level in the muscles. So LAC is lactic acid control. So you have some sensor that is giving you the lactic acid level in the muscles, and you're setting the breathing rate. See, at each level we are deciding what to control. There's 1 degree of freedom. The first option that we had was run at constant effort. We said, no, that's not a great idea, let's run at constant speed. We said, oh no, that's not a great idea, let's run at constant breathing rate. We said, no, even that is not a great idea, let's run at a constant lactic acid level in the control, and then we'll fix a set point for the lactic acid level, and hopefully this is, if not optimum, near optimum. So this constant lactic acid level running policy may be close to optimum, if not the optimum. Yeah. So you can see that when you have an unconstrained degree of freedom, what to control requires a lot of insight about the process. So you need process insight for developing optimal operating policy, particularly for unconstrained degrees of freedom. So in order to solve process control problems, what to control is a key decision, and it's a key decision because there are so many options in what can be controlled. However, the number of things that can be controlled is limited by the number of manipulated variables, and therefore you need to choose what process variables are controlled using the limited number of MVs. You need to wisely use your available degrees of freedom in the best possible manner, and in order to do so you need to understand fully what constitutes desirable process behavior, the control objectives and their prioritization. And in these decisions, economics is usually a major consideration in deciding what to control. And as we saw in our arguments, when you're trying to optimize the economic operation of a process, the optimum lies at multiple active constraints. So all the constraints that are active at the economic optimum should be controlled as tightly as possible. The tighter the control, the more squeezed is the variability, the closer you can drive the process operation to the constraint limit. Squeeze and shift. This is the squeeze and shift rule. And the second thing that we said was you need to find invariants corresponding to any unconstrained degrees of freedom whose optimum is not at a maximum or a minimum. It's somewhere in between. Corresponding to those degrees of freedom, what should we control so that the optimum value remains nearly invariant, nearly constant? And in order to make all these decisions, process understanding is crucial. I cannot overemphasize on the need for good process understanding to do good process control. So in that sense, once more, process control is the synthesis of all that you learn in chemical engineering. With this, we come to an end to this lecture. See you again next time.